Okay, so this is the basic plotting before going to advanced, and this is the basic parts of a plot. First, you have your data plotted, and we should have three things for each of the plots. You should have the axis labeled. Always, if you don't have, you don't know what's the label, just put X and Y data, but it's a good practice to do it. The title, as we did with the images, because if we run this code in a month from now, in a year from now, you're gonna know exactly what you're looking at. But if you don't put a title and you just have a figure, you're probably gonna be really lost about it. And if you have more than one data curve in the same plot, as you can see, we have a green one, a blue one, and a red one. You should have a legend in the plot. Each of these functions, it's right here. And at the end of this workshop, we're gonna give each of you a handout full of the functions that we use. Every single function is gonna be there. So our first challenge, you wanna see, you have two data, two strings of data, two vectors, and you want to see them at the same time, but they have very different scales, right? They have different orders of magnitude. So the pink data that's on the right, you can barely see the sinusoidal shape. On the left, I'm sorry. So you can barely see the shape, but you can see, but the yellow you do can see it because it's very big. But MATLAB allows you to do this, to have the left side one scale. So the left side in this case works only for the pink signal, and the right side works for the yellow signal. So you can know this because of the of the labels and the legend, and also in MATLAB you can set up the black screen, the black background, which is really, it looks cool for several types of plot. So these are the advanced plotting functions. Well, first, not advanced, but you need it whatsoever. It's importing. You need to import. The most common one is read matrix. There are other importing functions, but this one is the most optimized for most types of files. Then figure, we just use it a lot for imaging. And it just figures, just creates a new window. Then if you do y-axis left plot, and then y-axis right plot, you're gonna have this kind of image. Then if you have, when you have two variables and you want to do plotting, okay, you have two options. You have plot and you have scatter. With plot, you're gonna do, that means that your data has order. You have first data connected to the second, connected to the third. If you just want to show the points in a file, you use scatter. So we're gonna dive right into those real quick. And we go to MATLAB again. We go to this code called advanced plotting. We want to import the data I just spoke about. So this numerical data I spoke right here, you know, the cell size sample, the measurements of the lipid, the measurements of the protein, we're gonna plot them right now. So we're gonna begin with, we're gonna begin by doing, give me just 1 second. Okay, so you have data one. Just let me clear this from the workspace. Okay, you have data one. Data one, we're gonna use our function read matrix. Read matrix is gonna read some data from a file we tell it. In the zip file we sent to you, there's also these CSV files. CSV are the best files for MATLAB because they are really fast, much faster than Excel files, but all of them work. So first we're gonna do double y-axis access.csv. Don't forget the ending, the .csv or the .xls or the .txt. This is going to read us some data. And let me do this first. Let's open this CSV file so we can see what's inside if you haven't opened it. Okay, it's taking some time. Okay, so what we're seeing is that we have a time vector, which is the vector I told you. You are taking measurements every 6 hours. And then you have this concentrations, both strings of concentrations, okay, for lipid. So if we come to MATLAB, we're gonna divide it. So T, which is time, is gonna be equal to data1, which is our matrix, all the rows and only the first column. Okay, then lipid 1, it's gonna be the same data1, all the rows and the second column, and lipid 2 is gonna be data1, all the rows and the third column. If we run this right here, okay, we have T, lipid 1 and lipid 2. And let's do this real quick. Let's attempt to plot them. Let's plot T, comma, lipid 1 and T, comma, lipid 2. Okay, we run into a similar situation that we did in this scenario. We have a big function and a small function, and we cannot just appreciate them both at the same time. They look, one is really flat, but it's just because of the scale. So what we're going to do, we're going to go to MATLAB and we're going to plot them in the right way. So we're going to say figure, always begin with your figure, y-axis, left. We're going to plot first in the left and plot T, comma, lipid 1. Okay. We're going to plot T, comma, lipid 1 and then y-axis. Oh, and you have to put the Y label. Y label, it's going to be culture 1 concentration. Then we do the same thing, but with the right side. Y-axis, right, plot T, comma, lipid 2, and then Y label, culture 2 concentration. Okay, so as always, X label, we're gonna use time in seconds. Oh, let me add here the units, which is always cool. Okay, and a title. What title would this have? Would be concentration over time. Oh, time is in hours, not seconds. We run this and we get it. Okay, you see the difference between this and what we had before? Now we see they have very similar shapes, but they do not have the same scale. So for the blue one, we see we have this right here, and the red one we see we have this other scale right here. I was missing something, which is, as always, the legend is very important to put it. So we have culture 1, comma, culture 2. Okay, I missed this. Okay, now you see here, and there's a little trick I like to use. If you go to the legend and then put this, comma, you put location, right? And then you put here, northwest. And you run this guy. Oh, the legend just changed places. So in here, the legend, it's kind of in the middle of our thing. Here, here it's just on the other side. So this is a good trick. All right, I'm gonna follow with the 3D plots as 2D plots. So let me open this real quick. As you can see, let's say we have a three-dimensional array. What do I mean with that? We have a set of triplets. Every point that we get is a triplet. So for example, imagine something like a place in a plane and then a temperature, or a time, you know, some X data, some Y data, and then some Z data. So if you see the graph on the left, we have a three-dimensional plot, you know, a scatter plot in 3 dimensions of those. And I don't know about you, but I can actually get no information about this plot. This plot actually tells me nothing, the plot on the left, because I really don't know where each point. I would have to move the graph, see it around, you know, see different angles and see where's what point. And there are too many of them. I wouldn't have to, I couldn't know what to do. But if you see on the right, what I did is I made the same plot, you know, only X and Y data, right? So I put only the X and Y coordinates for the plot, but I made one adjustment. I made that the width, the radius of the marker of the circle that represents the point of data, it's bigger as the C data is bigger. So if my C data, it's bigger, as if you can see in the point 1, I'm sorry, 2 in X and 3 in Y, which be somewhere around here. So it's kind of big in the C direction. So it's probably this point maybe, or maybe this, depends on the angle. But I can see clearly that these 2 points and then these over here, they are about the same height. So that's what we're gonna do. We're gonna make some of the plots to be 3D, some of the 3D plots, the 3-dimensional vectors, represent them as 2-dimensional graphs and having some part of the graph as a 3rd dimension. So we're gonna go to MATLAB. 1 second. Here we go. So first, we need more data. The data we need, it's on another of the CSV files we sent to you on the zip. So if we get data 2, it's equal to read matrix, and then we say the name of the other file, which is 3dimensional .csv. All right, and now we have the protein. So what is this going to look like? What does this mean actually? We take the 3rd column. You can see which one is a protein if you open the CSV file and check them yourself. I actually won't do it because I know what's inside, but you can do that yourself. What's happening? What's happening here is that we have the time, right? The time we did at the beginning. You know, the same time with 6-hour intervals of we use to measure the performance of our cell culture. We get a concentration, right? Concentration of lipid. We have those as lipid 1 and lipid 2. right? We use them for the previous plotting exercise. And now we're adding a third one for one of those two for the number one, for culture number one. We made a protein measurement. We measure the concentration of some kind of protein, and we're going to see if it has an effect. Let's see how it looks like. So this is a protein. It has the same amount of points as concentration has. So I'm going to come here, and if I just come and plot, I say the function in MATLAB is plot3, and I say I want to plot3 of, give me 1 second to get this real quick. Okay, if I plot t, which is our time, we have it from the first data variable. Then I have comma lipid 1 comma protein. Okay, I have those three, and just plot3 for all of them. I run my code, and let's see what comes out. Okay, this file is not in our path. Let me, oh, it's because it's inside here. Okay. Oh, I made a typo with the dimensional. Let's see, I made a typo with the with the name of the file. So it's gonna run, and I'm gonna see at some point what is that distribution. Oh, come on, data 2. Okay, I think this should run now. Let's see. Okay, I have it. Can I understand something from here? Probably not. Even if I try to do the same thing with markers, I'm probably not going to understand anything from this plot. You see, I just see points. Even if I do a grid on, I can barely understand this. I mean, you can turn it around and see it, and then, you know, maybe come back to the beginning. I can barely understand it. So what are we going to do? We're going to do the same thing as plotting with the markers as plotting in 2D. And the third dimension comes as the size of the marker. Okay. So let me just add a few titles and labels. So title, we put 3D plot protein. Awesome. Then we come here and say, okay, our X label, it's time in hours. Our Y label, it's concentration in, I think it was millimolar. Yeah. And then we have, I think, I don't know, C label. Let me try this real quick. Okay, yeah, C label does exist. Then C label, protein concentration, say also millimolar. And we put here a grid on, and we go on. Plot the same thing. Okay, good. So what are we gonna do for the next one? The basic idea is you have to plot point by point. You have to plot each point by separate and have their width, the marker size, be a function of the protein concentration of the third vector. So I'm gonna do first the basic for loop for plotting everything, and then we're gonna add the functions. You're gonna see it real quick. So I say for, I'm gonna use double I, it's equal to the length of t, right? I put my end right here, and then I say, okay, what I want to do is plot t, right? T of I, the vector t, the point number I. Oh, I always get this wrong. I has to be a vector from 1, all the numbers through the length of t. So it's gonna be 1, 2, 3, 4, 5, up to whatever number there is of elements in t. Then plot t of I. Then I'm gonna say limit 1 of double I. Okay, that's what I'm gonna do. Then I want the points to be black and them to be points. I don't want them to be lines. I just want the single points. You can have a similar result with scatter, with the scatter function instead of. So I'm gonna use this. Now, if I just do this, I'm gonna get just points, right? Let's run this real quick. Okay, I just get points. They're somewhere around, but they're very small, so we can't see them. There's no rendering here. Let me add a figure. Okay. Oh, I forgot. Then you have to do hold on, because I just plotted 1 point. You have to put hold on so we can plot all of the points here. Okay, so we see all of the points plotted. Okay, good. Now we move on. When you have the plot function, you're gonna have additional modifications of the plot itself. For example, you have marker size. Okay, I spelled it right. Yes, I did. Okay, so I have marker size, and then I put, let me put mk size of double I. Mk size is gonna be a variable that I'm gonna create real quick. But so you understand the logic of this. What I'm doing for every single element of t, every single trial I made, every single measurement, I have the time of that measurement, then I have the concentration of lipid of that measurement, and then I'm gonna put the marker size, and this is gonna be a function. This is gonna be some operation I will do to the amount of protein. That's how we're gonna get this plot to work. So what is that function gonna be? Okay, let's deal with that function right now. So for every type of data, this is going to be different, because for some data you're going to have all the data quite packed quite nicely. So just multiply something, divide by something, that's going to work out. The normal marker size is 1. You can increase it, you can decrease it, that depends. But maybe if you square root it, if you take the some kind of function, it's gonna be easy. Some of them they're gonna be trickier. This one was a little tricky, so we made a function that at first is gonna look a little bit weird, but you're gonna understand real quick what's it for. So we're gonna put here magnitude protein. What happens is that the protein in the different levels, the magnitude is very different. It's very different. For example, if you see here, you can do this all the time in MATLAB. If you come to the variable window here and double click, you can see the variable.
Okay, I can see what's inside of the viral protein. So I can see that there are, some 0 0.1, 0 0.02, 0 0.02 again. And then you have very small numbers. These numbers are very, very small. 10 to the negative 12 to the negative 32. So if you're comparing this to this, that's several orders of magnitude different. So what I'm gonna do is I'm not gonna compare the number itself. I'm gonna compare the order of magnitude. That's all I'm gonna compare. How many orders of magnitude above or below are these numbers. That's the function I'm gonna use for the marker size. So how do I do that? With the log 10. That's how you get that's a way to get the order of magnitude. So I'm gonna do the floor, so I get whole numbers, and the log 10 of protein. This is gonna be, I put a comment, order of magnitude. Okay, so now I have the order of magnitude. Now, what I'm gonna do, I'm gonna put here mk size. This function is what's gonna go actually in here. In here, in the plot function, this is the function I'm gonna make. So I'm gonna have the magnitude protein. So what are we gonna do to this magnitude protein? We're gonna multiply by a number. So let me make a new variable called prop for proportion. I'm not gonna put 2. You can change this and see how the graph will change. I'm gonna say the proportionality times the magnitude of the protein. Okay. So what happens? I need to get the minimum. I need the one that's smaller to be 0. So I get minus the minimum of magnitude protein. Okay, so only these two lines, what they do, this line right here, this subtraction, it takes that my values go from the 0 to the maximum, to some maximum. That's okay. But now I don't want to plot a function with a marker size 0 because that's just going to be a point I'm not going to see. So I'm just going to add 1. So basically what's happening here, I'm subtracting the minimum of the whole vector to every single point of the vector. I'm adding 1, so the minimum is 1. And then I'm multiplying by self-proportionality that I can change right here. I can just change it just to see what happens. You can use 2, 2.5. There's many things you can use. So now this mk size is going to be a vector. And every time I plot something, the marker size of the function is going to be whatever that amount is. We found this by doing several trial and errors. So there's no easy, straightforward, one size fits all way to do this every time, but it's really useful to do it. So I'm gonna clear CLC and close all. Then I'm gonna run my code. There we go. So I see the points that are over here, they are larger, and as you come here, they get smaller. Do they actually make sense with everything I see? Maybe, maybe not. But actually, I see that the largest are around here, and the smallest are around here. This, it's a much better way to see the data than this, because I can see the same shape of the data if I just look it from the top. But what actually happens is that I cannot see how above or below what's the height of each of these points. I would have to do this then. But now I don't know which one is which. And this, it's very complicated. So what I do, it's make this plot on the right, so I can see everything at the same time. We did it. Now we're gonna put, as always, hold off, and our titles. Titles, 2D protein plot, and we're gonna put protein as marker size. Okay, now X label is gonna be time in hours, and our Y label, it's gonna be concentration in millimolar. Okay, let me put the apostrophes. Okay. I'm not missing anything. I'm not missing the legend. So real quick, one last time. Go to the protein as marker size, concentration, time. I have it. Okay, that's good. We did 2D plotting as 3D plotting. There are other things you can use for this type of 2D, 3D plot combination. For example, you can do the marker color. You can have a different color depending if you have categorical variables. If you have, you know, some kind of a darker color means something, lighter color means something for every point. You can also have a color scale and use, you know, some point of the color scale depending on some variable that looks in your color map. You know, when you then the color maps, you can get that variable like that. Or you can use something else. For example, the width of the line. If you actually plot a line, you can have the width of the line be a function of something else. There are several things you can do for this kind of study, and there is no finite way of doing them. It's just your creativity and whatever you want to give it to the plot. And we have one more type of plot before we finish, which is not a particularly advanced plot itself, but there's many things you can do about it in MATLAB. So, which is the histogram. What the histogram does, it's just take one variable and you can see how many times the values repeat in itself. So I'm gonna go, there's one more data we have to import. I'm gonna call it data 3. And I'm gonna do read matrix, and I have histogram.csv. As you can see, there is a histogram.csv right here. And 1 second. Okay. So because that one in particular, it's just one vector. We don't have many vectors in it. Just have one vector, and that's what we're gonna do. So data 3, it's gonna be my histogram, and I'm gonna do here a figure, and then the MATLAB makes it really easy for us. It's just histogram of data 3. There's one function that's called hist. Don't use it. MATLAB doesn't have the histogram, is an improved version of that function. And we're gonna see how it looks. Okay, what does this mean? Let's show data 3 vector right here. So you see, data 3 vectors are numbers that go from 12, 10, 9. There are different numbers we see, okay? And we want to say this is a survey of the cell size. We want to know What's the size of the cells? This is measured in microns. So which one are this? Are these made for? You know, how many 14s? You know, we see some 14s right here, another right here, 15. But we want to know where are the values clustered. In the histogram, we can see that very easily. You can see that you have a big one between the values of 12 and 15. There are 17 numbers in your vector, 17 elements that have a value between 12 and 15. You see that, you know, you can see them in the histogram every time, and it's a really easy plot to go along. I like if we have face color, comma, green. I like the green face color for the histogram. And we make a title of histogram of cell size. We have our X label being radius. It's measured in the micrometer scale. This slash mu. Right here, it will draw the Greek letter mu. There's a MATLAB page with all the symbols and Greek letters you can use for your labels. And our Y label, we'll call it free count. We're gonna run this again. Okay, we see histogram cell size, and you see there's a little mu right here, and we have our histogram. You can have more variables, more inputs, so you can have, for example, a custom size of the bins. You can say, instead of grouping them in 3x3 bins, I want them to be 1x1. So all the numbers between 9 and 10, then 10 and 11, then 11 and 12. And there are more options for every single function we use here. So please go to our MathWorks documentation. There's always more to do. And if we come back right here to take a look, these are the functions we use. If you have 3D variables, right? You know, an actual function, a mathematical function instead of data. You can use measure it and plot the surface, or do a p-color, pseudo color plot. And then there's this last really nice thing, which is to change the background of the plot to black. So let me try that real quick. So actually, I won't try it right now, but that's something I leave here for you to try.